Welcome to The Explainer. Today, we are jumping straight into a cosmic journey that stretches from our very own backyard all the way to the edge of the observable universe. We're going to see how a recent massive flood of groundbreaking observations is completely rewriting our understanding of the cosmos. And we're going to start with a very specific, mind-bending mystery about alien moons, specifically observing a moon-forming disk around the gas giant C-Cha-B that astronomers have been trying to figure out for decades. So take just a second to consider our own solar system. Look at Jupiter. Jupiter has nearly 100 moons, right? But they're incredibly diverse. You've got Io, which is violently covered in volcanoes, and literally right next door, you have Europa, which hides this massive icy subsurface ocean. Or look at Saturn's moon Titan, choked with thick, carbon-rich smog. How in the world did moons forming around the exact same planet end up so wildly different from each other? Well, the James Webb Space Telescope, JWST, has just found the answer by looking at a baby gas giant 625 light-years away from Earth.
Section 1. Birth of Alien Moons.
Okay, let's look at this young baby gas giant known as CT-Cha-B. Carnegie Science's Sierra Grant used over 42 hours of observation time to capture the first-ever detailed spectroscopy of a moon-forming circumplanetary disk. Basically, she read the chemical fingerprints in the light of the swirling halo of gas and dust directly surrounding this baby planet, the exact material that's eventually going to clump together to form its moons. When astronomers compared the massive disk of material orbiting the host star to the smaller localized disk orbiting the baby planet, they found a completely stark contrast. The host star's disk, absolutely zero detectable carbon molecules. But the disk around the baby planet, it actually contains 7 different carbon-bearing molecules, including highly complex ones like benzene. If you were to animate a little stickman trying to breathe out there on a future moon, they'd be surrounded by an incredibly complex chemical soup that doesn't even exist around the host star. This brilliantly illustrates that circumplanetary environments undergo intense, localized, and accelerated chemical processing on million-year timescales. The chemistry happening right around the planet is completely disconnected from the wider solar system, and that localized processing is exactly why moons forming around the same planet can develop such wildly different geological and chemical compositions. But here's the thing. This rapid, localized chemical complexity doesn't just stop at alien moons. It extends to entire planets. Thanks to JWST, astronomers are suddenly finding these impossible planets that break literally all of our established rules for how the universe is supposed to work. And it's forcing us to completely revise our planetary formation models. Let's look at a few of these incredible plot twists. First up, TOI 5205b. This is a Jupiter-sized planet orbiting a tiny M-dwarf star, a star that's only 40% the mass of our sun. A planet this big absolutely should not exist around a star this small. Astronomer Shubham Kanodia found that the inside of this planet is 10 times more metal-rich than its outer atmosphere. It's got an unmixed core, meaning it formed in a way completely different from the gas giants in our own solar system. Then we have WASP 94ab. It's a hot Jupiter 700 light-years away, where the weather is just bizarre. It has clouds made of rock-like magnesium silicate that gather every morning, but as the planet rotates into 1,000-degree heat, those rock clouds literally vaporize, leaving clear skies in the evening. And finally, the wildest of them all, PSRJ 2322-650b. This is a planet orbiting a rapidly spinning dead star. The gravity is so incredibly intense, it pulls the planet into the shape of a lemon, and its atmosphere is pure molecular carbon. It literally rains diamonds. We have absolutely no idea how this world came to exist.
Section 2. The Ingredients for Life.
So, how do these highly localized chemicals eventually spark life? Well, to answer that, we need to bring it right back into our own solar system. NASA's OSIRIS-REx spacecraft returned a pristine sample from asteroid Bennu, which is essentially a time capsule from 4.5 billion years ago. And the findings? They are absolutely staggering. Researchers found 14 of the 20 amino acids required for life on Earth to make proteins. They found all 5 nucleobases needed to encode DNA and RNA. They also detected exceptionally high levels of ammonia, which, if you have the right conditions, reacts with formaldehyde to form these exact complex molecules. But even more amazingly, they found 11 distinct minerals forming a complete set of evaporites. These are the salts left behind when water evaporates. Bennu's parent body didn't just have the building blocks of life, it had the salty liquid water broth needed to mix them all together. This completely changes how we view these ancient rocks. As Tim McCoy from the Smithsonian notes, these evaporites, minerals like calcite, halite, and sylvite, have never been seen together like this in an extraterrestrial sample. It proves that the interior of Bennu's ancient parent body wasn't just briefly damp. It was warm enough to support a liquid saltwater environment for thousands of years, maybe more. It was perfectly suited to kickstart the chemistry of life, long before the Earth had even finished forming. But do these rich environments exist beyond our solar system? The answer is yes. We know this for sure because of an interstellar comet named 3I/Atlas that recently passed through our neighborhood. It was observed simultaneously by the Europa Clipper and JWST spacecraft, with one looking at the night side and one at the day side. Compared to our native solar system comets, this interstellar visitor had highly elevated levels of carbon monoxide, carbon dioxide, and methane. This is direct proof that these cold, carbon-heavy, life precursor environments are just drifting through deep space, too. Section 3. The gravitational cosmic hum. We've looked at planets, moons, and asteroids, but what about the mechanics of our galaxy itself? Astronomers have recently confirmed that the very fabric of our galaxy is humming with a constant background noise. Now, to hear a hum like this, you need a detector the size of a galaxy. Enter the pulsar timing array. Pulsars are rapidly spinning dead stars that sweep radio beams past Earth with the insane precision of an atomic clock. The Nanograv collaboration spent 15 years meticulously monitoring 67 of these millisecond pulsars all across the Milky Way. They were looking for nanosecond variations in the arrival times of these pulses. Why? Because that would indicate that the actual fabric of space-time between us and the pulsar was being stretched and squeezed by passing ultra-low frequency nanohertz gravitational waves. And after 15 years of looking, they actually found it. As Stephen Taylor points out, this is opening a completely new window into astrophysics. But what exactly is causing this massive stretching of spacetime? The answer is supermassive black holes. When massive galaxies collide, their central black holes, each weighing billions of times the mass of our sun, sink to the center and begin to orbit each other. This orbital dance literally vibrates spacetime, kind of like two really heavy, waltzing dancers rhythmically vibrating a wooden dance floor. Now think about this. Over the entire 13.8 billion year history of our universe, hundreds of thousands of these supermassive black hole binaries have danced and merged. The ripples from all those ancient massive collisions overlap and wash over us today, much like ripples from a handful of pebbles tossed into a pond. That overlapping energy is exactly what creates this continuous nanohertz cosmic hum echoing through our galaxy right now.
Section 4. The universe expansion mystery.
Let's zoom all the way out to the very edge of the universe to confront a growing crisis in cosmology. It's called the Hubble tension. The Hubble constant is the rate at which the universe is currently expanding. It's the linchpin for understanding the age and the history of everything. But we have a huge problem on our hands. Our measurements simply aren't matching up. When we predict the expansion rate using the cosmic microwave background, the fading glow of the early universe, we get one number. But when we directly measure the expansion rate using stars in our local modern universe, we get a faster number. This discrepancy is a big deal because it suggests our fundamental physics models might actually be broken. To figure out who is right, competing teams of astronomers are now using JWST to measure distances using different stellar milestones. One team uses Cepheid variables, which are basically pulsating stars. Another team looks at the tip of the red giant branch and JLGB stars, essentially using different types of aging, highly luminous stars as cosmic yardsticks. The hope was that JWST's incredible infrared resolution would show that our older Hubble Space Telescope measurements of these stars were simply blurry or confused, and that the whole tension would just disappear. But here is the ultimate plot twist. The JWST verdict is in, and it confirmed that the older Hubble telescope wasn't broken at all. JWST proved with 8 sigma significance, meaning it is a virtual mathematical certainty, that we aren't confusing Cepheids with other stars. Now, while there is still some debate over potential biases between the different star measurement methods, the core discrepancy remains very real. The local universe really is expanding faster than the early universe predicts, and the main takeaway here is profound. We might need entirely undiscovered physics, perhaps something related to dark energy or dark matter, to explain how our universe actually works. Section 5. Our next cosmic eyes. To solve these massive mysteries, from those localized moon-forming disks to a humming, unexpectedly expanding universe, we're going to need new tools. So here is the near-future timeline for our next cosmic eyes. In 2025, the massive Vera C. Rubin Observatory down in Chile expects its first light. In 2026, the Nancy Grace Roman Space Telescope will begin its Cycle 1 imaging from orbit. And looking just a bit further ahead to 2031, missions like Psyche will be wrapping up their close-up planetary orbital surveys. Let's look at what the Virusi-Rubin Observatory brings to the table. This facility houses the largest camera ever built. Instead of just staring at one tiny patch of sky, it will scan the entire visible southern sky every 3 to 4 days. It's basically creating an ultra-high-definition time-lapse movie of the universe. It's expected to generate up to 10 million real-time alerts per night, instantly pinging scientists around the world when a transient event occurs. Like, say, a distant supermassive black hole suddenly tearing apart a star. And complementing that from orbit will be the Nancy Grace Roman Space Telescope. Roman is going to conduct a deep, space-based, all-sky near-infrared survey. It's actually expected to discover over 100,000 new exoplanets just by watching them transit their stars. It's equipped with this advanced coronagraph that can literally block out a host star's light, allowing us to directly image planets a billion times fainter than their stars. And by monitoring microlensing events, where the gravity of a star acts like a giant magnifying glass, Roman will map out the structure of dark matter and probe the dark energy that is driving our universe's mysterious expansion. Which brings us to our final thought. We live in a cosmos where carbon-rich ingredients for life are swirling in the disks of baby moons and trapped in the salty evaporites of ancient asteroids. We live in a galaxy that is physically humming from the collisions of supermassive black holes, inside a universe expanding faster than our current physics can even explain. With the Rubin Observatory and the Roman Space Telescope about to open their eyes, what impossible thing do you think we'll find tomorrow? Thank you so much for joining me on this explainer. Keep looking up, and I'll catch you next time.